Hello, good morning, everyone, or good afternoon, good day, good night. I'm very pleased to introduce today's speaker, Michael Friedlander. Michael has been doing some of the most interesting work in optimization, especially applied to data science and signal processing. Michael received his PhD in operations research from Stanford University in 2002. From there, he went to Argonne National Lab as a Wilkinson Fellow. And then in 2004, he joined University of British Columbia, where he's been ever since. He is professor in both the CS and the math departments, and he currently holds the IBM Professor of Computational Mathematics. Also, he's currently serving as at UBC as a director of the Institute for Applied Math. He's very active in SIAM. You probably have seen him around organizing meetings and doing editorial work. And he's currently the program director of the SIAM activity group in optimization. So today, Michael is going to talk about polar deconvolution of mixed signals. So Michael, without further ado, please go ahead.
Thanks for that nice introduction, Fadili. And thanks for Dio and all the rest of the organizers for the opportunity to talk about this, my latest work in the deconvolution of mixed signals. And I have two goals with this talk. One is to tell you about a really interesting problem in statistical signal processing that involves the separation of signals that have been, you're observing the superposition of signals, and we want to separate those signals through some efficient procedure. And the second thing I'd like to tell you is, really it's sort of a hidden agenda, is I'd like to tell you about a really interesting technique in convex analysis having to do with convolution, a special kind of infemal convolution, which is a way of mixing convex functions in order to produce another convex function that has some interesting properties. And this field of infemal convolution really has a lot of beautiful geometry. And I always continue to be sort of astonished by sort of the beautiful geometry that's in infemal convolution and how well it lends itself to computation. And I think this deconvolution of mixed signals is an interesting application of those ideas. And I want to acknowledge before I start my collaborators who really are the driving force behind this particular work. My students Zhenan and my postdocs Halyun, Jeong, and Babhru, Joshi are really, in fact, responsible for a lot of this work. Okay, I think the way that I'm going to introduce, what I'll do is I'll start out with a few examples to tell you, to give you a sense of what the demixing problem, signal demixing problem is, before I get into the specifics of it. And all of these images you're seeing were all recovered using the same sort of the same code, the same algorithm, and it's an efficient code in the sense that it's in particular it's efficient in space. So it only requires space that's proportional to the size of the data, which is a sort of an important feature when we're talking about large-scale applications. We'd like it to the storage requirements to scale proportionally to the size of the data, because ultimately we have to hold the data in some place on the computer memory, or have access to it. So here's a problem that we might call separating spikes and sinusoids. Here this image X is a superposition. Maybe it's a photo of the night sky, and it's a superposition of stars. And of course, in the background, you see there's a picture of a galaxy. And so this superposition of two signals they're morphologically distinct, in the sense that the stars can be modeled as spikes, as a spiky signal, but the galaxy that's behind it has a smooth structure to it. And so we can see that there's really two signal components, X1 and X2, that form this superposition. And we can model X1 as being sparse in let's say, the Dirac basis. So here it'd just be it's the sum of single element matrices. Actually, there should be a weight in front of this thing that would depend on each of the EIJ pairs, and each EIJ would give a particular instance. And then, of course, there's the background part, and here the assumption is that this part of the image is sparse in frequency. And so here we have a two-dimensional DCT transform, which takes the elements and moves them into the frequency domain. And this really is an old problem, and it really goes back to Chen, Donahoe, and Saunders, who talked about basis pursuit denoising, and then Donahoe and Huo who give conditions for which you can do this this sort of recovery. Here's a similar application. Here we want to separate background from foreground from noise. So here's a picture. Let's say a simple picture of a chessboard. And really, you can think of this as having three signals that are superposed. One signal is the chessboard itself, that's the background. Then there's the pieces that are overlaid on top. And then there's some noise. This maybe we know what the structure of that noise is. So there's really three things that are going on. We really want to, if we can separate the noise and the foreground from background, then we could reconstitute the image. So in particular, we want to take the image with the noise and split it up into a sparse component, which would be the pieces themselves, and then a low rank component, which would be the chessboard. And so here, again, this is similar to what we had before in the sparse image. We're really thinking this part of the image as as a sparse superposition of atoms, which as I had before, which would be from very simple rank 1 matrices. And the low rank part is this sparse superposition of a few rank 1 matrices. Okay, and this separation of background from foreground is what's sometimes called a robust principal components. And this follows from work that was looked at by Chandrasekaran et al. When they were looking at atomic decompositions, and this is the paper on robust PCA by Candes and Lee, Ma, and Wright in 2009. Here's, I'll give you this, I think this is the last one. Here's a multi-scale low-rank decomposition from an application by Ong and Lustig. Again, this was run using the same code base as from the other pictures. And here we have our image. We can see that there's a multi-scale structure here, right? There's part components that are think of them as spikes, they're just single pixels, and then there's smaller structures, sort of intermediate structures, and then there's sort of a large background structure. And so we want to decompose into these different scales. And so each one of these different scales, again, can be thought of as a sparse superposition of low-rank matrices of different sizes. So for example, this should be 4i to -1. So here, these would be 1x1s, superposition of 1x1 matrices. This would be a superposition of 4x4s, 16x16, 64x64 matrices, for example. This is a small example. So what ties all of these applications together is there is an implicit assumption on that each one of the constituent signals that represents the superposition is sparsely representable in some dictionary. And these dictionaries are somehow morphologically distinct because it would be impossible to separate the signals two sparse signals if they were both sparse in the same kind of way. I assume Fadil, folks will chime in if they have any questions. Feel free to do so. Okay. All right, so here's the approach that I'll take for explaining this material. I'll tell you about, ultimately I want to tell you about the full signal demixing problem, where we have some observations which are really, these observations B are are measurements that we make through some measurement operator, a linear measurement operator of each one of these constituent signals. So each one of these is a signal that are all superposed through a measurement operator in order to produce this final observation. And then possibly there's noise. And this line of analysis that we take, in some sense, largely follows McCoy and Trop, who really pioneered this idea of using random rotations to introduce this notion of incoherence, which would guarantee when you can do the recovery. And we're sort of following that, a lot of that line of analysis, though we're using ideas from polar convolution, which allow us a few useful, both somewhat analytically convenient techniques to use that are particular to polar convolution, and also allow us to generate, to use an efficient algorithm, which is going to be based on the conditional gradients. So I'll tell you about the signal demixing problem. First, I'll start by talking about a simplified version. I want to tell you something about polar convolution and then how it fits in with conditional gradients. And this idea of polar convolution I find fascinating. It's a way of constructing regularizers by mixing the level sets of the simpler regularizers. And here, for example, this would be a simple, let's say, the level set for a two norm. And this would be like, let's consider it for the level set for a weighted infinity norm. And the polar convolution is a kind of a mixture of the one norm and the infinity norm. That would be the level set, and we can create new regularizers in this way. Okay. Here's the simplest signal demixing problem, and here I've taken away the measurement operator, and I've just assumed that we have two signals that we're going to demix. Though in general, we want to really look for an arbitrary demixing an arbitrary number of signals that have been compressed in some way through the measurement process. And the underlying assumption is that each one of these individual components has some sort of sparse atomic representation in terms of some atomic set. So what a sparse atomic decomposition would mean that the first signal x1 is some non-negative combination. So here the non-negative coefficient Ca, there's a coefficient Ca for every atom inside the allowable atomic set. So here we would say, in the language of convex analysis, here we would say that Xi is in the conic hull of a particular atomic set. And so examples of atomic sets, we've seen some of them already, some trivial ones. Sparse n vectors, of course, are conic combinations of the basis vectors, trivially. And the Cj's would just be the absolute value of the components. And then it's the sparse combination of all of the, or it's the non-negative combination of all the signed canonical vectors. And similarly, low-rank matrices would be a sparse superposition. Here are the coefficients, which would be the eigenvalues of rank 1 outer products that would have unit norm. And of course, one way of attaining this sort of decomposition is through an eigenvalue decomposition. Though there are though here we're not assuming that that X would necessarily have an orthogonal decomposition, or not necessarily the sparsest. So this is we think of this under the class of problems called morphological components analysis. And the idea is that each one of these constituent signals represents, has a different morphology to it. And this assumption is crucial because we need the different morphologies in order to be able to succeed in breaking up the signal, in order to detect what the different parts of the signal are. And one way to get a handle on what it means to have a different morphology is to think about the incoherence between the morphologies. And I'll talk about a way of characterizing the incoherence between the morphologies. Essentially, it having to do with the angle between descent cones that are defined by the level sets, or the convex hull of these atomic sets define level sets to certain functions. And as long as those descent cones, which would give us a certain measure of optimality, as long as those descent cones are well separated in some sense, then we would declare them incoherent. and that would be sufficient condition in order to be able to separate the signal. Any questions so far before I continue? All right, Fadil, I assume you'll let me know if there are. Let me talk about regularizing for sparsity. I think it's now pretty well established that gauge functions to atomic sets have this sparsifying property. So what's a gauge function to an atomic set? So remember, the atomic set A really contains these simpler elements, these atoms, for which we want to use to construct each one of the constituent signals. And so this gauge function is defined for any set of vectors, and it doesn't have to be a finite set. It could be an infinite set, as it was with the set of low-rank matrices. It could be uncountably infinite, or it could be finite. And what we're asking for is, we're constructing this function gamma A, the gauge to A, and evaluating the element X. We're asking over all valid decompositions, over all valid conic decompositions, because we insist that the coefficients are non-negative. We want to find the set of coefficients whose sum is minimal. And gauge functions really are generalizations of norms that we use all the time. So in particular, every norm can be represented as a gauge function. Also all semi-norms. The crucial bit is it allows, this definition of a gauge generalizes it sufficiently that it allows for, let's say, asymmetry in the definition of the gauge. It also allows for infinite values, which is a useful way to exclude parts of the domain that are not of interest to us. So if we take, for example, the set of signed canonical unit vectors as our base, as our atomic set, then we get the one norm. Right, and we could, we could just write it out as it's writing this expression out. It's really taking the infimum over the coefficients. In this case, the coefficients of the decomposition are just the modulus of each one of the components of X, and the atoms are one of the particular basis vectors with a corresponding sign. The semi-definite trace norm. Of course, this would only be defined over W's that are positive semi-definite, because if it's indefinite, it can't be represented. It can't be represented as a conic combination of these atoms. So strictly speaking, I should add the indicator function to the semi-definite cone here. And here, the gauge formulation, I was taking the sum of the coefficients. The coefficients are the elements lambda, and which have to be non-negative, and then there's the rank 1 outer products. And here's the crucial, I wanted to give you some of the geometry of these gauges. So these gauges, the epigraph to this gauge is a cone, because it's a positively homogeneous function. So it's necessarily conic. And we can think of, really this is the convex hull of my atomic set, because my atomic set doesn't necessarily need to be convex. It's really a slice. This atomic set is really the unit slice of this cone, of this epigraph. And through a property of polarity, which is looking at all the angles that make a non-negative less than or equal to inner product with all the vectors in this cone, we get the polar cone. And then we could also slice that cone at the unit level set. And that slice, we can regard that as a kind of an atomic set as well, as a kind of a companion atomic set. That's the polar. So apolar is defined to be the polar of that slice. And in fact, that itself produces a gauge. So it's the epigraph to the gauge of apolar, which turns out to be the support function. So this is a way of generalizing the notion of a dual norm. And this polarity operation will be crucial in this decomposition process. Okay, so how do we combine let's talk about combining the regularizers. So if we come back here, we could have ways of constructing these gauge functions. So given if we have a prior on on the atomic set for which each component is sparsely representable, we need to talk about how we're going to combine each one of those priors in order to represent the sparse decomposition for each one of the constituent signals that we're hoping to recover. So again, I'll just talk about two signals, but everything I'll say really applies to K signals. So the underlying assumption is we have this prior that each one of these constituent signals is AI sparse. And the typical approach for combining the regularizers, or the gauges that would give us sparsity in each one of these constituent signals, would be through just maybe combining through some weighted sum the different gauges. So here I might want to minimize. I'm going to try to find vectors x1 and x2 that satisfy the data. I'm just going to ignore the noise here for a moment. So given x1's, oops, this should be xs, because xs sharp is the signal that we've observed. And we want to find components x1 and x2. And here we're combining the gauge functions just through a simple addition. So here to be the gauge, we want sparsity with respect to the first atomic set. And then there's some sort of weighting to acknowledge that they might have different magnitudes, the gauge to the second atomic set. And this is sort of the typical approach. And in fact, this corresponds to infemal sum convolution. We are in fact convolving these two different functions. So and the result, the value, right? So we take XS, this little optimization problem has a value to it for any given XS sharp. And the value of that is a function itself. And you can show that the value of that is itself a gauge. And in fact, it's the union of all of the atomic sets. And in fact, the epigraph of this gauge is really the direct sum or the vector sum of the epigraphs of each one of these individual gauges. So we see this in practice. For example, on robust PCA, this is the paper I mentioned by Kendes, Lee, Ma, and Wright, where we have some matrix Y and we want to decompose Y as into a low rank and a sparse components. There's possibly noise, so we don't want to match our reconstruction exactly with the data. It has to be within some sort of fidelity term alpha. And we might have a term for a component wise on the one norm to try to encourage sparsity in this component, plus the nuclear norm, which would try to encourage low rank, and this would be the sum of the singular values. Okay. So I want to talk about a different way now of combining the regularizers that uses this idea of polar convolution. So it's the same setup. We're going to assume that each one of the constituent signals xi sharp is AI sparse. So we have this prior about the representability of each one of these components. And we just need the simple observation that if each one of the components xi sharp is AI sparse, in other words, it's sparsely representable in that particular atomic set, then the sums of the signals is necessarily therefore sparsely representable in the sum of the atomic sets. So here, when I add these atomic sets, these are sets in Rn. When I add them, I'm thinking about the vector sum or the Markovsky sum of each one of these atomic sets. So then, if we then believe that the sums of the atomics of the sums of the signals is some AI sparse, then and if we believe that that gauges are good promoters of sparsity, that leads us naturally to say, well, let's form the gauge to the sum of atomic sets, different than what we had before. And so the gauge to the sum of atomic sets is also a kind of infemal convolution, except it's not an infemal sum convolution before. Before we were taking the sums of these atomic sets, or the weighted sums, and here we're taking the max. So we're taking the infemum of the max. And again, we ask that the individual components have to satisfy the data here. Okay, just here's just a little graphic about what I mean by the Minkowski sum of the individual atomic sets. And this gauge function to the sum, this infemal convolution, has a kind of a minimax sparsity property. What I mean by that is, I put sparse in quotes because we're using the value of the gauge synonymously with the sparsity of as a stand-in for sparsity. So if we believe that low gauge values mean you have sparse elements, then the minimizers that evaluate, that achieve this gauge convolution, this polar convolution of gauges, are minimax sparse in the sense that the gauge values of each one of the elements that satisfies, that solves this problem here, it must be lower than the gauge value for any other feasible xi. So among all feasible components that might satisfy the data, the ones that satisfy this problem are necessarily minimal. So that's the sense that I mean that the solutions to this problem are minimax sparse. This minimax sparse property does not necessarily hold for infemal sum convolution, which is what's typically used. The other interesting property, and this is really useful for the analysis and for an algorithm implementation, is that gauges decompose under this polarity operation, this dualizing operation, or when we talk about a dual norm, or we talk about a dual gauge, or the polar gauge in particular, it decomposes. So the gauge, if I want to take the dual gauge or the polar gauge, think of this as, if gauges are not familiar to you, think of this as a norm, and here we're taking the dual norm. Is that it decomposes. So the polar of the gauge to A1 plus A2, this infemal, the polar convolution of these two gauges, of the individual gauges, gauge A1 and gauge A2, in fact, is a support function to the polars, to the sums of the polars. And I should have left I should have done one more step here and then shown you that the support function to the sums of the polars is in fact the sums of the support functions. This term here is equal to the support function of A1 polar plus the support function for A2 polar. So it lets us treat them separately. Here I have a simple example. Here what I'm taking is the polar convolution, this little notation for polar convolution. And I'm just doing it for the P norm and the Q norm. And when I dualize the polar convolution of the P norm and the Q norm, I'm going to get the sum of the dual norms. So the Q norm would be dual to P, and the P norm would be dual to Q. So there's a simple example of how the polar convolution decouples under this polarity operation. Okay, so this is just a simple example for norms, but it holds, of course, much more generally for all gauges. All right, so let's go to the noisy demixing model now. How do we handle noise? Because we don't just observe necessarily the superposition of the individual components. We observe the superposition, and then there's some noise, and we maybe make the assumption that the noise is bounded. So we would need a slightly different deconvolution problem. I'll call it deconvolution denoising, where we're taking the inf of the max as we had before, but then we don't insist that the sums of the x's have to satisfy B. In fact, we don't want them to. That just has to do it within some tolerance. And so we can ask, let's say in the noiseless case, so I need some sort of conditions to account for this fact that I don't have this minimax property directly anymore because I'm relaxing this constraint. So here make the observation which really McCoy and Trop in 2013 was a crucial part of their work, and also I think Chandrasekaran et al. In their atomic decomposition paper would say that in the sum convolution, but it also holds true in this polar deconvolution case, that the individual components are optimal for this problem here, and this would be in the noiseless case, if and only if these descent cones only don't intersect. They only intersect trivially. So what does it mean for these descent cones at AI at xi sharp? Essentially, that means that there is no downhill direction. There's no way to move away from xi sharp and reduce the gauge values. And so then you're necessarily optimal. But this condition is too strong because, of course, we do have noise. And so when we have noise, it's possible that, that these descent cones are arbitrarily close to each other in some sense. They still may not intersect except at zero, except at the origin. But we want a kind of a separation in order to allow for the possibility of noise. And so what we're going to do, and this is where we depart from some of the earlier work, is we measure the separation of cones. We have a quantity to measure the separation of cones. In fact, we're going to look at the angle between the cones. And we're going to say that these two cones are beta incoherent if the angle satisfies a certain, if this property holds between beta and 0, 1. So in particular, if beta is equal to 1, then these guys would essentially be as close as they can to each other. Now, what will be important here is that sparsity is related to the width of the cone. So we assume that there are ways of quantifying this, as particularly look at the Chandrasekaran et al. Paper. If it's the sparser a vector is, so there's a measure of width of the cone is smaller. And so if you have sparse vectors, these cones are narrower. And so it's more likely that they are incoherent in that sense. And so that's why sparsity is an important assumption, because it is what helps us encourage this incoherence between the cones. Okay, so what's one way to introduce incoherence? Because we don't necessarily assume that that the signals that we're trying to separate are incoherent. If they're not necessarily incoherent, we can introduce that incoherence by randomly rotating the signals. And one situation where you might be able to randomly rotate these signals would be if you have a bunch of measurement devices that are producing the signals, and before they mix, each one of these devices would rotate its signal, would apply some sort of random rotation. Then they're mixed. And then at the receiving end, if we have knowledge about these rotations, we can then decouple it because we have knowledge of what the source rotation was on the original signal. So it's same setup as we had before. We have the superposition of the signals under noise, and now we're going to assume that the superpositions are really are the rotations of each one of the individual signals under some bounded noise. And we can show that if under some random rotations qi, we're drawing random vectors from the special orthogonal group of random matrices, orthogonal matrices, that the descent cones for each signal, for each rotated signal, with respect to its rotated atomic set, because we have to move its reference frame along with it, that they're in fact beta incoherent with high probability, where we can actually characterize the incoherence in terms of the a universal constant, the dimension, the ambient dimension of the signal, and some measure of the total conic width of all of the descent cones. So of course, the more cones that you're mixing, or the wider the cones are, let's say the less sparse the signals are, then the smaller the incoherence would be. And so what we can then show is that the polar deconvolution, that this deconvolution problem will in fact, there should have been a brace here, that this polar deconvolution in fact yields solutions which are not too far from the original signals. And not too far meaning that they are within that they are within this factor with high probability, where alpha is the noise and beta is our measure of incoherence. Okay, so now we have a result that says if we randomly rotate these signals, that guarantees us with probability, with high probability, some measure of incoherence, and that measure of incoherence also then guarantees us a bound on the quality of the reconstruction. Okay, so of course we could do this for the general model, for a random measurement model, where now we have a measurement operator in front of it. The setup is the same. I'm just going to assume that the signals are already rotated at this point. The only thing that extra piece of information we're going to need is, and that I haven't talked about before, was that we have information on the relative signal magnitudes with respect to each one of the atomic sets. We don't need, so this is we need a way of balancing the way in which we measure the magnitudes. So here we know that they're all relative here to the first signal. That's arbitrary. And that we're taking the atomic sets and we're taking their weighted sum. And now we have a two-stage process. The first stage is to decompress. And decompress, we can really think of this as a compressed sensing problem, where we're minimizing the gauge to the aggregate atomic set. And here the point of this problem is to recover this aggregate signal. So we call this just a decompression phase. And then once we have this aggregate, then we would do the deconvolution phase to use the solution for the decompression inside of the deconvolution in order to recover the constituent signals, and everything we said before applies. So we're really separating the process into decompression and then deconvolution. And here we have the main result is that if the signals are randomly rotated, then the decompression followed by the deconvolution phase produces with high probability constituent signals that are close to the original signals with this possible error. So here we have alpha is the error in the measurement, and we could see this before, this same constants that we had before, the total width and the ambient dimension. And what I want to show you here is that we factored this confirmed in theory. Here, what we here is doing is each one of these little pictures, this somehow got flipped. Each one of these little pictures on this axis is the number of measurements. Here is the ambient dimension, and here as we get closer to a white square, it means that the error in recovering each one of the constituent signals, the sort of maximum error, is low. So white or low or light entries are good. And so see, as the number of signals that we're trying to demix goes up, we do need to be in this regime in a higher number of measurements, but also in a higher ambient space. If we embed it in our signals in a higher ambient space, then they're more likely to be incoherent as when we do the random rotations. And this red curve is the theoretical minimum required number of measurements, and we can see that we're under which we can't recover, and we can see that there is kind of a phase transition that does follow the theory, though it is pessimistic here. And this yellow curve is the minimum number is the smallest ambient dimension that we can get away with. We also see that similar transition here. Okay, so I have, I think, 5 or 10 minutes. I want to tell you about how the conditional gradient method plays very nicely with this polar convolution. So let me just summarize the conditional gradient method for a generic problem. Here we're minimizing just a convex function, differentiable function, over some convex set, and in particular, in the case we're interested in, we're minimizing it over the convex hull of this vector sum of each one of these atomic sets. And so what is the standard conditional gradient method? At every iteration, you need to compute the gradient or the negative gradient. And what you want to do is expose the face. You want to expose the face of the atomic set that's exposed by the vector z. And then when you grab one of those atoms in the face, and what you'll do is let's say in a vanilla version of conditional gradient is you grab your atom and you adjoin it to some working set, and then you're gonna choose the next iterate somewhere in the convex hull of the collection of atoms that you've computed so far. This is a general version, of course. And this includes simpler versions, which would mean some sort of line search or maybe a constant step size. So what is this facial exposures line? So the way to think about it is Z is a descent direction, and that vector Z defines a set of hyperplanes, and what we want to do is sweep that hyperplane out. And so we sweep it out as far as we're solving essentially trying to find a subdifferential of the support function. And the crucial bit here is that this vector Z exposes, you see the maximum hyperplane exposes a vector A. And what you can show is that then when it exposes the vector A from an atomic set, which is the sum, that Z also exposes the atoms from the individual atomic sets. So here, the same vector Z also exposes an atom from A2, and it also exposes an atom from A1, which is to say that this facial operation decomposes. So because we're looking at the face of the sum of atomic sets is equal to the sums of the faces, which means we don't have to deal with trying to compute something, trying to compute this gauge function for the full aggregate atomic set. We only have to have oracles for computing the faces for the individual atomic sets. So implementing this for the particular case, there's a lot of savings that can happen. This is for the deconvolution problem. This will work for the decompression and the deconvolution problem. The gradient is now just the M adjoint to the residual. It's a negative gradient, so I don't have a minus there. Here, R is just the residual in satisfying this equation. At every iteration, I would grab an atom that's exposed in each one of the atomic sets, and all of this can happen in parallel for each one of the individual atoms. I could have written for 1 to K. And then we could do a simple line search to try to minimize the least squares objective between the original data model and the data to give us parameters, to update parameters. The interesting thing about using least conditional gradient for least squares is I actually don't need to store the atoms. I actually don't even need to store the primal variable. You can see I just need to have, all I really need to have here is the action of my linear operator on the atom. And this is especially important if the atom, for example, is an outer product, which would be hard to store or hard to manipulate. And all I really need is the operation of M on this atom, which lives in the data space. And so this is a purely dual, dual implementation because we don't have the primal iterate. But the important thing is that the components, as this iteration converges, as the ZKs converge to something, this ZK exposes all of the atoms that are inside of Xi. And so as an after the fact, I can go and get all the atoms in the particular constituent vectors Xi. And the complexity of this iteration, in order to get this misfit to within epsilon, is O of 1 over epsilon, and I only need O of the data for space. I'm sweeping some things under the rug because there are extra parameters here that I need to fiddle with in order to make sure that that I satisfy this property, but it doesn't change the complexity that I'm showing you here. I think I'll leave you with some references that explain the work that I've been doing in gauge optimization and its applications to statistical signal processing and image processing. This last paper here, this is the paper that talks about this polar deconvolution, but it really depends on a lot of the theory that's been developed in earlier work. I think I'll leave it at that, and I thank you for listening, and I'm glad to take any questions that you might have.
Thank you so much, Michael, for a very interesting and very clear talk. Are there any questions from the audience? Please raise your hand and then I will unmute you.
Well, I recognize a few names on the attendee list.
Yeah, we can unmute them anywhere, and we can start talking to them. Michael, while people are still thinking about their questions, this is very interesting. How does this apply to the cocktail party problem, or does it apply?
Oh, that's a good question. There might be many definitions of the cocktail problem, but I think you're right. I think it's related. And the cocktail problem, as I understand it, you're sort of listening to a bunch of conversations at once, and you're trying to decouple those conversations. I don't know what the standard techniques are for that particular problem, but in order to use this approach, we'd have to have some sort of prior on each one of the individual voices. So I might have to know, for example, what frequencies your voice is in versus somebody else's voice. So I need to have that prior, and that's what happens here.
Right.
I have to have this prior on how incoherent those individual voices are. But I can only imagine that in the standard cocktail problem, that some sort of incoherence assumption must be made there.
It is. Yeah, one of the most popular algorithm for that is the ICA, independent component analysis.
Okay.
So yeah, but this brings a really interesting new technique or new point of view for that very classical problem, which is very important in designs of hearing aids.
Of course.
Do the panelists have any questions? This is one of those weird things where people are a little shy. So how difficult, you mentioned that the algorithm that you design is very straightforward. And do you have codes that people can try out?
Yeah, I'd be happy to share code. It's a single code base. It's written in Julia. And it's efficient in the sense that the complexity really here, this 1 over epsilon calls each iteration, where is all the cost? The cost is all in doing products with your operator, and depending on the application, this can be costly. So you have to apply this, and then we have to do this facial exposure. So, for example, if your atomic set is a set of rank 1 matrices, then exposing a face on the set of rank 1 matrices corresponds to a maximum eigenvalue computation. So there you'd have to fire up some sort of Lanczos process in order to find a maximum eigenvalue. That procedure itself can sometimes be expensive. There are other cases. If we're looking at more esoteric atomic sets, for example, a collection of infinite sinusoids that are parameterized by a scalar, that shows up in an application called super resolution, and there that exposure operation corresponds to solving a small semi-definite program. So that's sort of that extreme of cost. If you're looking at the other extreme, like if it's the set of signed unit vectors, because we're looking for sparse vectors, then that's just a simple, that's an O of n operation to just find the maximum element. So there's a whole range of costs to this facial exposure that'll depend on the particular atomic set.
I see.
The crucial part of this algorithm, though, is that we don't, even though we start out by modeling this as a gauge, which is the sum to atomic sets, which is probably something that we can't usually compute. It turns out we don't need to ever compute it. We only ever need to compute this polar operation for each one of the individual atomic sets. And we almost always know how to do that for lots of the interesting atomic sets.
In that example that you where you reveal the phase transition, what was the example there?
Oh, these phase transition curves? Yeah, these are very small just because we wanted to, because this is very intensive. We had to run each problem is run multiple times in order to get an empirical estimate of the average. So these are just vectors that are of length n, which have a fixed sparsity. So just fixed sparsity. So we want to separate k vectors that are 5 sparse, and then it's. So here, all the atomic set is very simple. The atomic set is just the signed unit vectors, and the facial operation is just finding a maximal element of your gradient at every iteration.
Okay. Yeah.
This theory doesn't depend on the particular atomic sets in particular, which is why we just chose a simple example in order to be able to generate these phase transitions, which are quite computationally expensive.
Well, it doesn't look like there's any question. Maybe because your talk is so clear.
Well, I'll just point people to. Oops, I didn't mean to do that. I'll just point people to these references in case they'd like to learn more.
Yeah.
Actually, I think we just put this. We just posted this on arXiv yesterday. So if you do want to take a look at this latest paper, check on my website in a day or two, and then we'll have the actual number once it's assigned to us.
Okay. Fresh off the print.
That's right.
Well, if there are no questions from the audience, I think we're just. Oh, there's somebody who raised a hand here, Victor Portella. All right, go ahead, Victor.
Hey, thanks. Michael, thanks for the talk. It was really clear. One thing that I was thinking, like, since nobody is asking questions, it may be a silly question, but when you say like, oh, we are assuming that the signals are randomly rotated, and when you apply it to real problems, like for separating the background from the chess problem and the pieces, do you just like apply it to the problem itself, or you kind of try to apply random rotations to the signals, try to apply the algorithm and like unrotate them to get the original ones? Like I'm just curious if like this assumption is like just a not so crazy assumption, or if you actually rotate the signals in applications.
Thank you for that question. I think Victor's asking is, when do we need to do this random rotations? When is it reasonable to do so, and do we always need to do it? So if we're trying to separate signals that have the same morphology, for example, if in the example where I'm doing, I'm just separating 5, sparse vectors. Unless the signals are somehow distinct, in the particular case, unless we would have to guarantee, for example, that the sparsity patterns don't overlap, because if all signals were exactly 5 sparse in exactly the same way, there'd be no hope of demixing those. So in that situation where the atomic sets are not naturally separated, we would have to either assume that they're rotated or introduce the rotation explicitly. So, and that's not, of course, possible in all applications. Fadil mentioned the cocktail problem. There, we don't have the luxury of going up to somebody and saying, please rotate your signal before you send it to me. So that's obviously not possible. But if we're designing a system where we want to, where we have a bunch of devices and they all want to communicate over the same channel, then we could engineer the system so that they rotate their signals before they send them through the channel. So that would be a particular application. But if we're looking at other applications, something like this, where we're looking at the multi-scale decomposition, then there's a sort of a natural incoherence between the atomic sets, because of the scales at which each one is at a vastly different scale. And so there we don't need to introduce the rotation. And Ong and Lustig in particular, they're giving incoherence conditions to show that you can do recovery in this case. So I think to answer your question simply, either you have this incoherence naturally, or you introduce it through this rotation process.
Oh, I see. Yeah, it's clear. Thanks a lot for the
Thanks for that question.
for the talk. Yeah, thanks.
Other last questions? Well, if not, I just want to thank you again, Michael, for waking up so early in Vancouver and giving this wonderful talk.
Just in time to take my son to school. Well, thank you so much, Fadil, and the others for the invitation, for organizing this very nice seminar.
All right.
Thank
See you
you.
later.
Bye-bye.
Thanks
Bye.
a lot. Bye.